We're headed into our Applied Biomechanics course, KPE 327. The name of the course really matters. There are studies of mechanics, there are studies of biomechanics, and then there are applied biomechanical studies. And because we have particularly shared interest in body movement and propulsion of objects for competition or for accomplishment of work tasks, we're going to try to be systematic in our application of the physics of movement so that you as a healthcare practitioner and a purveyor of sound coaching techniques and teaching techniques would have the equipment, the insight to analyze movement and move forward. To my way of thinking, this sequence of movement, of throwing the javelin, really summarizes the intricacies of a ballistic movement that is highly sequential. And so you'll find on E-Class the PowerPoint and the video that's embedded in this PowerPoint allows you to see the world record holder in the javelin. And I'd like you to have opinions about why he's the best in the world. So view that, study the PowerPoint, and then I've given you, I think it's about 10 pages of reading in the Hall Biomechanics textbook on linear kinematics. And I'll talk to you about kinematics here at the end of my presentation, my video presentation. So be a student of this. What do you think after watching this sequence of movement? Oh, it's balletic. And if you and I could throw the javelin a long ways, or our mother could, or our second cousin or our teammate could throw it, it's breathtaking. And knowing what it takes in the context of gravity, in the context of interfacing with the ground, or the support surface with spike shoes, all of those are mitigating circumstances that need to be controlled. Another aspect of really understanding a javelin throw or activities in which the body itself is propelled or objects are propelled is the interplay between angular motion that produces linear motion, or turn that around, linear motion that when the force is applied eccentrically, meaning away from the center of mass, it causes rotation. We need to be students of those things. Now think about it. If the javelin thrower did not have the capacity to move into extremes of angular motion, I know you know a great deal about this, having come out of structural kinesiology, what muscle motors cock and deaccelerate and which muscle motors accelerate the levers of the body. And we're going to add into this appropriate trajectories that maximize displacement. We're going to study about the coefficient of friction. The movement really begins in the feet. The study of momentum. How does this person get down the runway and accelerate to the place where, along with the cocking and the ballistic motion that we've studied in the past, gets optimal results for the entire system. But really, his success is judged upon the displacement, the maximal displacement of that javelin. Well, here we are. Mechanics have some element of just raw physics. The mechanics of architecture and engineering, the mechanics of structure. If you become a physician assistant or an orthopedic doctor, then you're going to need to know the biomechanics of the structures of the body. When there are arthroplasties or joint replacement, trust me, as they plot their strategy about which size joint and which entry and so forth. They're talking about biomechanics. Really, our intention is to talk about functional biomechanics, and that apply to you getting up out of bed, maybe apply to you as the physical therapist who's teaching a person who's a biplegic, a person who's paralyzed and doesn't have use of their legs but they have their arms, how to transfer from toilet to cane or to chair. All of those things, the person who teaches swimming, what are the best mechanical principles for teaching a senior citizen to get out of the pool when they don't have enough strength. Otherwise, they've really got to have great ergonomics. So we're going to be working on those areas. And then I love this. All of these handouts are available to you on the PowerPoint that are posted under KPE 270 Module 1. And you see that we can divide the field, the overall umbrella of mechanics, into statics, really where there's not perceptible movement, and dynamics. Obviously, you're in the Department of Kinesiology. This is where we hang out. Dynamics. We're students of movement. Now we're headed into a study of physics, the movement that is defined by force and by time, displacement, velocity, and acceleration. And there's two primary areas that we study. One is kinematics and the other is kinetics. In this video, I want to jump up on top of this and the readings that I have for you to be prepared for critical thinking and group performance in class is in the area of kinematics. Maybe I just say a word here. Right now, forever and always, know that the area of study in mechanical dynamics known as kinetics, which we'll get to on Thursday, that's the study of forces. Kinetics means the study of forces, and you'll see these sub-areas are linear application or receiving of linear force, and then also angular. Doesn't mean much maybe to you yet, but it will. But coming up now, I'm going to emphasize the parameters of kinematics, which include time, simply done in with the units of measure being seconds, displacement being measured in feet or meters, velocity, feet or meters per second, and acceleration, which has to do with, for every second, how much velocity is being applied. That means there's a change in velocity. Acceleration means change in velocity. And we'll study this in the forms of linear applications of these kinematic principles and angular. So the units of measure for angular are, for displacement, time is still second, displacement are degrees, and then degrees per second would be how we express angular velocity, and then degrees per second, or degrees per second squared is the expression of acceleration. As you do your reading, I think it starts at page 319 in the Hall book. I've put that both on the announcement and also in Unit 1. So make sure that you do your reading. Maybe I'll do it this way. This is how I want to treat you. When you're done preparing for class, you're going to know about the kinematic principles of time, displacement, velocity, and acceleration. That's what you're going to know. Okay? The definition of kinematics is the description of the appearance of motion using terms of time, displacement, velocity, and acceleration. You come to class with having operational definitions and knowing the units of measure for each of those parameters. So here we go. We set down right now in our YouTube video here together the units of measure for time are seconds. It's used to calculate speed and velocity, and you can see that speed is distance divided by time. Now, I'm not in this YouTube video going to tell you the difference between distance and displacement. I'd like you to figure that out based upon your reading. And I don't know if I'll have somebody stand up and deliver, or we'll do, a 3x5 quiz or whatever. It's just that please be accountable to know the difference between displacement and distance. This is a vector quantity, and and this is not a vector quantity. Okay. All right. And then displacement. The units of measure are either meters or feet. In the shorthand of kinematics, displacement can be either represented by S or by D. Okay? S or D. And then the definition of displacement is the change in position, and it is a vector quantity. That means that all the summary movement can be graphically depicted as a vector which shows magnitude and direction. And then velocity is very simply defined as the displacement in a given amount of time. And so the units of measure, if we're dealing with, if we're measuring in meters, it would be how long it takes you to cover those meters in units of seconds. So the units of measure for velocity are meters per second. If you're using the English system, it would be feet per second, very simply. And then knowing that, it makes sense to you that this shorthand for velocity equals delta means the change in position. You've gone from point A to point B. That's a distance. You can subtract what your original distance was, 0, from your final distance, and that is the change in position. You started a stopwatch at 0 and it elapsed over a certain period of time, and that's the denominator. So change in position divided by change in time, or we could say position 2 minus position 1 divided by the change in time. That gives you velocity equals distance or displacement divided by time. One thing that I want to share with you is that bar V means the change of, it means the average velocity, so a little bar over the V. And then acceleration is the change of velocity. It's the rate of change in velocity. So for every second that a person moves at a velocity, remember a velocity is displacement divided by time, for every second of that velocity, that represents the acceleration. And so change delta velocity divided by delta time. And this works out to be that the units of measure for change in velocity is meters per second squared, or another way to think of it is it's the meters per second, which is velocity, divided by total seconds of moving at that velocity. That represents velocity per second. So you've gotten started, you're looking at this, and you have your readings, and so we'll come in and do some movement. We'll have stopwatches, dress for activity. Okay, Lord bless you. We're underway with Applied Biomechanics.